animation, and this is a topic that actually goes way back, as you can see on this 1972 footage from the first computer-generated movie. And at the time, in order to produce this animation, the authors had to manually digitize a real hand model, like you can see on the bottom video, by carefully measuring all the positions of the points of this model. So this was a lot of work, right? But nowadays, of course, the computer animation pipeline is much more sophisticated, and in order to produce this kind of animation, generally, we instead manipulate the digital skeleton of a virtual model such as this one. So this is an improvement compared to 1972, of course, but our issue is that the usual tools of computer animation still do not fit perfectly well with the hand models we are interested in. And that is mainly because hands, as well as their 3D models, are highly articulated. So if we look at those usual techniques applied to hand models, there is forward kinematics, for instance, when you manipulate each bone of the skeleton one after another. And there is also the more advanced inverse kinematics, which instead consists in only choosing the end position of each fingertip, and the bones automatically follow. And it seems that whatever the technique, they require to apply many adjustments, and that for the many keyframes of the animation. So this makes hand animation a time-consuming task. But we can look at some alternative techniques for easing the hand animation process. There is motion capture, of course, which is natural since you perform the motion yourself, but it often relies on expensive hardware, such as data gloves here, or on the contrary, on low-cost sensors, like the lip motion, which are in practice not accurate enough for hand animation. Then there has been some research on using tangible devices for this. This one, for example, takes the shape of a human hand, and it's manipulated like a puppet in order to drive a virtual model. But you have to use your two hands to control a single hand model, so it's not completely efficient. And here is another example. It's a ball covered with pressure sensors, and it recognizes the posture of the user's hand. But it's limited to grasping postures, and we want a system that is a bit more generic. So considering those limitations, what we developed is a system dedicated to hand animation that we call THING. And in summary, THING is about controlling 3D hand models by first putting our hand on a multi-touch tablet, and then performing the motion ourselves, for example, by making a fist or pointing a finger like this. So the benefits of this approach is that it's natural, since you perform the motion, and in that sense, it's a bit similar to motion capture, but we don't rely on expensive hardware. It also provides parallelism, since multi-touch input lets us control many parameters at the same time, and this is especially valuable when dealing with those complex hand models. And finally, it's based on multi-touch tablets, which are low cost and common and easy to integrate into the workflow of 3D animators. So in this video here, you can see our system being used, and I'm going to go through the three components that make this kind of interaction possible. The first one is that since human hands are quite complex, THING relies on a simplified parameterization of it that I'm going to describe. Then I will talk a bit about the custom armature that we use in the end in the 3D editor to reflect those parameters. And finally, I will describe the multi-touch interface that lets us control this hand model in an intuitive manner. So let's start with the first one. And the main challenge that we have is that human hands have 27 degrees of freedom, and that is a lot of parameters to handle at the same time. So to make the control of our hand models more manageable, we instead use a reduced model with only 16 degrees of freedom. And the simplification occurs on different parts of the hand. First, the real finger of a real hand has 4 degrees of freedom, since each of its joints can do this curling motion, and the base joint can also do this lateral motion called adduction. But in reality, if you look closely, the motion of the different joints is not so strictly independent, and there is a strong coupling between them. So in our model, we only have 2 degrees of freedom at the base of each finger, one for flexion, one for adduction. And the flexion of the following joint is derived from the flexion of the root joint. Then another difference in our model is that we consider the thumb as a regular finger, whereas a real thumb has a special 3 degrees of freedom joint at its base. So this indeed restricts the postures that we can adopt, but we will address this at the end. All in all, this gives us 16 degrees of freedom, and we can split those into two different frames. There is a local frame that includes the local finger configuration, and there is also the global frame, which includes the position and orientation of the hand in space. So I'm going to focus first on the local frame. So as I mentioned, each finger has only 2 degrees of freedom, so we can formulate the state of a single finger with two parameters. There is one for flexion, one for adduction. And in order to reflect those parameters into our hand model in the 3D editor, we have to bind the model to specific 3D components. So each virtual finger is associated with an inverse kinematics target that will guide its motion. And it's also associated to a Bezier curve that defines the trajectory of the target. So with this setup, flexing a finger is only a matter of moving the inverse kinematics target with respect to that flexion parameter, so it moves along the trajectory. And adducting a finger laterally is only a matter of moving the target perpendicularly to the trajectory with respect to that adduction parameter and the control points of the trajectory. So this leaves us with 2 degrees of freedom per finger for a total of 10, which is still a challenging amount of degrees of freedom to control. So in order to make this more transparent, we have a user interface that is consistent with our task, and it takes the form of a set of sliders that appear under the user's finger when he first put his hand on the tablet, and then the user only had to perform himself those flexion and adduction motion relatively to the slider to modify those parameters and control the hand model. So in practice, we differentiate between those 2 degrees of freedom by looking at the displacement of the user's finger along different directions. So for flexion, for instance, without going into too much details, we simply consider the flexion, the displacement of the user's finger along the slider. And for adduction, we only look at the displacement of the user's finger laterally to the slider. So we saw how to control this local frame, which included the local finger configuration. And now for controlling the global frame, which includes the global position and orientation of the hand, we experimented with 2 different variations of our technique. The first one, we called it MobileTHING, and it's about letting the tablet handle all of the degrees of freedom. So to move and rotate your hand model, you simply move and tilt the tablet in space. And the second one, we called it DesktopTHING, is about delegating the control of this global frame to the usual tools of computer animation. So typically you use the tablet to control the fingers of the hand, and you switch to a mouse and keyboard combination to control the position and orientation of the hand. So the idea here is that it's very tempting to try to integrate all of the degrees of freedom on a single device, like we did with the mobile version on the left, but we are also aware that it could become very tiring to hold the tablet in the air. So this is why we also did this alternative hybrid version. And those 2 will be compared in the user study that follow. But just before that, here are some use cases showing what we can do with our approach. On the top, you can see the realization of an animation that features some throwing and catching a ball. And you can see the final result on the right. And for reference, it took approximately 7 minutes to realize, which is quite reasonable. And on the bottom is another scenario in which we control the 2 hands of a bimanual character. And here we choose which hand to control by either putting the left hand or right hand on the multitouch tablet. So let's go to the user study. Here we wanted to assess how our approach compared to other more established animation techniques. So we asked users to complete a docking task in which they controlled a hand model, the realistically looking one on the video here, and they had to reproduce the posture of a reference model, the yellow one here. And for each trial we recorded the completion time, since we are interested into the performance of our approach, and we also asked users to fill a subjective questionnaire. And we had 3 different conditions. The first one corresponds to the traditional way of doing computer animation. So users had a keyboard and a computer mouse, and they had to control the hand by using an inverse kinematic setup hand. So this means they only chose the hand position of each fingertip and the global position and orientation of the hand with the mouse. Then the second condition is motion capture with a data glove. So we use the 5DT glove with some external sensors for the position and orientation of the user's wrist. And finally, there is our technique, the mobile version, which lets the tablet handle all of the degrees of freedom. And for fairness, we also used the same sensors as with the data glove instead of the internal sensors of the tablet. We asked participants to reproduce 4 different poses, and they were always presented in the same order of increasing complexity. So for reference, the first one only required the flexion of a single finger, and the last one was more complex. It required to translate, rotate, and flex different fingers to different degrees. And we had 12 participants. So here are the results from the first user study. We found that the data glove and our approach both outperformed the traditional mouse technique, And we also found that there was no significant differences in terms of performance between the specialized data glove and our approach, which is the first good result. Then regarding the participant feedback, there was no significant differences between our approach and the others. However, we got some pretty negative comments informally from some users, and some mentioned that our approach felt less precise than the mouse and keyboard combination, and some also mentioned that holding the tablet in the air was tiring. So for this reason, we ran a second user study, in which this time we compared the two versions that we proposed. So the idea here was to see if users would prefer the hybrid version, which mix computer mouse and multi-touch tablet, and if this version would provide similar performance. So we still had three conditions. We kept the computer mouse condition as a control condition. We still had the mobile version, and we also had the desktop hybrid version. In order to shorten the experiment, because it was a bit long, we removed the first pause, since the results from the first user study showed that it was quite easy to reach anywhere, and we had 12 new participants. And here are the results. So we found that both versions of our approach showed higher performance than the mouse, which is consistent with the first user study, but that's except for pause number 2, and we suspect that this is because there was a learning effect, and we removed the first pause to gain some time. And the other result is that there was no significant differences in terms of performance between the two versions of our approach, the mobile one and the hybrid one, which uses a computer mouse. So this is what we wanted to check for. And finally, regarding the subjective appreciation from users, we found that there was an overall preference for the desktop version, the hybrid one, and it was rated better than the computer mouse for ease of use and speed, and it was also rated better than the mobile version for precision and fatigue. So in order to summarize, I presented THING, which is a system dedicated to hand animation, and it relies on a multi-touch tablet on which you put your hand to control the fingers of a virtual hand model. And we ran 2 user studies, and the main results were that we had performance similar to those of a specialized data glove and better than those of a traditional mouse. And the desktop version, which conjointly used a computer mouse with a multi-touch tablet, was preferred over the mobile version, while still maintaining the same level of performance. So in the end, this lets us think that THING could be an alternative to the traditional way of doing computer animation, and it could be especially appreciated by newcomers in 3D animation, since the traditional way of doing manual computer animation, such as forward kinematics or inverse kinematics, can be seen as quite intimidating. Of course, there are still some limitations to address, and that's for future work. The first one is that with the hybrid version, we force users to switch back and forth between the tablet and the computer mouse, and this transition induces a homing time that is bad for performance. So one solution to get rid of this will be to remove the mouse altogether. For instance, one possibility will be to use the multi-touch tablet as a touchpad to control the cursor on the main screen. Another bigger limitation that we have right now is that since we simplified the modelization of the hand, we are missing some degrees of freedom, and some postures cannot be reproduced. For instance, when you grab an object, the shape of the object can in reality block some parts of the finger, but those are some postures that we cannot reproduce with our system right now. So one possibility will be to consider more inputs to alter the trajectories of each finger, for example, pressure sensing, but the current state of pressure sensing on commercial tablets is still not really accurate. So yet another solution will be to instead exploit the semantic of the interaction. For instance, we could imagine if we want to grab a 3D object, adapt the trajectories of each finger to fit the shape of the object in order to grab it more realistically. So just to finish, here are some applications. There's computer animation, of course, for games or for movies. And another field that we're interested into exploring with our system is 3D interaction, and especially virtual reality, because this is a field in which it is often necessary to be able to control a virtual hand for real-time 3D interaction, and to be able to travel within large immersive workspace while holding the input device. And this is maybe the field in which the mobile version of our approach could prove most useful. So thank you for your attention. I'm finished. This is just a last example of what we did with the system, and if you have any questions, I'll be happy to answer them. Thank you.
Have you considered? No, look. Okay. No, it's a long walk. Have you considered looking at the almost touching? There are quite a few tablets that can detect almost touching events. Like Microsoft Surface can do that.
Thank you for the question. No, we didn't look into that. To be honest, I'm not familiar with the technology actually. If it's compatible with current commercial tablets, well, we should try it. But one of the goals of this project was to provide computer animation, human hand animation on very common and low-cost devices. So this is why we used it was like a Samsung tablet or something very simple that everybody can buy. So if this technology is compatible with this kind of tablet, we will try it. We will try it, yes.